Okay, so hello everyone. I will be starting the class now. So welcome to the first class of Grammar of Code's Div3 CP workshop. In this class, I'll be discussing complexity analysis. And if you have any questions while I'm teaching, you can unmute and ask me. Okay, so to start,
Mainak, you are muted.
wait, yeah, sorry. Yeah, okay, so what is complexity analysis basically? So we want to see how the time and memory requirements of our program, how do they change as we change our input parameters? Okay, so if say we have an input n and we want to see that if we say double n or we do 4 times n, how will the complexity how will the time taken by a program to run, how will that change? So usually we analyze the time complexity of the program, but using the techniques for this analysis, we can also analyze the memory complexity of the program. Uh, Usually, though, we don't analyze the memory complexity because usually the memory limit is large enough that we don't need to worry about it. Okay. So yeah, we need to analyze the complexity again because in competitive programming, we need our programs to run within a given time limit and a given memory limit. Like you'll usually see that time limit is given as say 1 second and memory limit is given as say 256 megabytes. So 256 megabytes is quite large, but this time limit of 1 second for an input of say 10 to the power 5 or 10 to the power 6, it's going to be like you have to think carefully about how much time your program is going to take. All right, on to the main question that how do we analyze the time complexity of a program? So for this, we use something that is called big O notation. So roughly speaking, big O tells us that like it tells that within this bound. In other words, it gives us an upper bound on how the program will behave. Right. So say by often, like by often, when we say often, we say that the complexity of the program is linear. So that means if our input size doubles, then the runtime of the program will also double. Like if say for a given input, our program takes half a second. If we are given 2 times that input, it will take 1 second. Now, if we have O of n squared, we say that is a quadratic runtime. That means if n doubles, the runtime of the program will double 4 times. So one variable. Uh, so yeah, so like we can have say O of n log m. So for example, maybe in say some graph algorithms, we will teach graph theory later on. But in some graph algorithms, you will have say a runtime that depends on both with the number of vertices and edges. So just to give an example. Okay. Next up, we'll just give a brief overview of what is the formal definition of this big O. Usually, you do not need to think about this. Usually, when we talk about big O, we just want a rough estimate of how much time a program will take. We usually don't go deep into like what is the exact values and such. Great. So let's just read what it says. So it says that f of n is equals to O of gn if and only if there exists some constant c and n naught such that f of n is less than equals to c times gn for all n greater than equals to n naught. So just to demonstrate what this means, I'll just draw a graph here. So basically, we are trying to say that, let's say we have a graph of this is the time taken and this is the size of our input n. So say we have some f of n that scales like this, right? And now we have some g of n, which we are taking to be this nice function that just grows like this. So this is like our c times g of n, and this is our f of n. Now you see at this particular point at n naught, this function always is greater than this function. Uh, so in this case, we can say that f of n is equals to O of gn. So like, let's take a more concrete example. Let's say we have something, some fx is equals to say some polynomial like 2 of x square plus 3x. So for this, what should be like, what is a good simple candidate for gn? Does anyone want to give it a try? Or you can unmute and say if you want. Anyone?
X square.
X square, yeah. X square is a good candidate. And why can we take x square? Okay, so basically we can take x square because like if you take say some large say 5 times x square, that is like we want that to be greater than equals to 2x. Like obviously you can see that at for some large value of x, this is going to grow much faster than this. So yeah, x square is a good value, and it is also like it's also a tight bound, like in the sense that if you pick x, that wouldn't be a good answer because we know like x square is going to grow like this and x is going to grow like this. So yeah, x square is a good answer for this. Any questions if you have anyone? Oh, okay, so yeah, so
Hello?
there are similar
Yes.
definitions for these things called, yeah, this it's someone
Yeah.
unmute.
Why not one? Why not x? Uh, why g of x is not equal to x?
Yeah, because you see that if you say pick say any x, say c times x, then you want c times x to be greater than equals to 2 times x square plus 3x for all n naught, that is for all n that is greater than some specific n naught. Right. So but you think about it. If you look at the graph of this function, if you take at x square for large values of x, it will like grow like this. Now it will grow quadratically like a parabola. But this x will still
Yes,
just
yes,
grow
got
like a straight line. So at some point, after some point, this function will always be actually greater than this function, isn't it? But we want the opposite to be true, but that is not happening. So we can't pick x here. Did you get it?
Yes, yes. Thank you for clarification.
Yeah. Okay, so there are similar definitions for big theta and big omega. Big theta means it's bounded above and below. Say like so like big theta, we can say that if this is our function, then we can find some two functions, no, one function like c1g and one function c2g, so that this f always stays between these two functions. That is we draw it like this, big theta. And for big omega, I think, yeah, it's this symbol. We are trying to say that if we have f, then we can find some CG. You know, it's kind of a very similar definition as we have given for big O. So usually we do not talk about big theta and big omega in competitive programming. So I'm not talking about them in much detail. Okay, so it's just good to know. Okay, next slide. Right. So we want a rule of thumb for estimating. what time complexity is good for our program. So like usually if our program makes around 10 to the power 8 operations, like we say it can be 1.25 into 10 to the power 8, like if it's little bigger, it doesn't matter usually. But usually around 10 to the power 8 operations for 1 second time limit. So if your time limit is given as 1 second, a good like uh, bound is that you take a 10 to the power 8. But sometimes you can take 10 to the power 9 if your operations are simple, like addition and multiplication. Subtraction is also included. But what isn't included is division and taking modulo. So like uh, if you go into the details, like in the architecture, like hardware, then you will see that division and modulo are actually kind of difficult operations. So they take more time. So if you are using those, don't expect to like be able to achieve 10 to the power 9. But usually to be on the safe side, we take 10 to the power 8 only. Okay. So now, now these are some common time complexities and some typical values of n that will be given in the input, right? So usually how we use big O is that, like, say if our n is given as less than equals to say 500, and our algorithm is of n square, then we just do n square is equals to 500 times 500. That is something like 25 into 10 to the power 4. So around 2.5 into 10 to the power 5. So that is very safely within. Did someone unmute? Okay, yeah, no, yeah. Uh, okay, if no one unmuted, yeah. So, so yeah, this 2.5 into 10 to the power 5 is very safely within 10 to the power 8. So it doesn't really matter. We are good. Okay, so hold on. Yeah, no, right. So we just erase this. Yeah. So coming back to this table, we have some common time complexities are, say, O of 1. O of 1 basically means constant time complexity. So any questions?
Here f of x is time complexity, right?
What? Can you say again?
F, f of n is time complexity, right?
Yeah, like our time complexity is going to be denoted by O of f of n, where f of n is some function that we have. Yeah, so so like in here, our f of n is like or 1, or f of n is say log n, and yeah, let's say it's equals to x to the power n, actually confusing, n to the power k. So this is like a polynomial runtime. This is like a logarithmic runtime. This is a constant runtime. So so this is a table of some common time complexities you'll come across. So constant time, say you are doing some integer a is equals to 2500. So assigning a variable is something that takes constant time. Like you won't take a lot of time to do that. Uh, Something which takes logarithmic time is, say, binary search. Like you take an array, you take a sorted array, and then you search for the middle element. If it's not there, then you look in the right half or the left half. So every time you're splitting the size of the array in half, so n by 2, n by 4, have to say n by 2x to the power x equals 1. So the number of steps is going to be like x. So x is equals to like log base 2 of n. So that is an example of a algorithm with, say, logarithmic time complexity. So typically, the maximum value of n you will see is 10 to the power 18. So like if you take log of 10 to the power 18, that is something like what 60. I mean, we are talking about log base 2 here. Usually when we talk about log, we talk about log base 2 only. Like it doesn't matter. Like you know how to convert from one base to another. It's just a constant. So Yeah. So it's not, it's 60. 60 is much smaller than a 10 to the power 8. So this is what you'll typically see. Okay. So then we have say O of n or O of n log n. O of n, you can say if you are just going iterating over the array. So you go from left to right using a for loop, that is O of n. Or n log n, you know there is sorting. Sorting usually takes O of n log n. There is merge sort, quick sort. So if your expected solution, like if your solution has this kind of time complexity, then typically the value of n you will see is 10 to the power 6 maximum. Um, like, and similarly, like you will have n square and then you will have n cube, 2 to the power n factorial. So n factorial is when you're say going over all the permutations of an array. 2 to the power n is when say you're going over all possible subsets, because you know there are 2 to the power n possible subsets. So yeah, so if you like take this table and calculate each of these, like say O of n cube, we take 500 cube, and that is I think 1.25 into 10 to the power 8. And you can see that this is around 10 to the power 8. So you will see that for each of these values, it's more or less following the rule of thumb. So that is one thing. And like you may encounter other complexities, like say n log n in case of sieve. And there are some algorithms which can take square root of n time also. So yeah, so that's basically what I wanted to say here. Any questions?
Hello.
Yeah.
Uh, why we have limited O of 1 for input size to be lesser than 10 to the 18?
Yeah, like why 10 to the power 18? That's because in like if you are using C++ or C, like as you will usually use, usually we use C++ only. So the long int data type, that can actually fit up to like I think 9 into 10 to the power 18 around. So like usually in competitive programming websites, you will see it's given as 10 to the power 18 only, so that you can just do calculations in long int only. So that's why I've given 10 to the power 18. If you go any bigger than that, then you'll have to start using big integers, and then there is a whole lot of work there. Like you may have to write your own big integer class or switch to Python. So yeah, but basically it's just that this limitation of long int can only be less than equals to this much. Nothing else. Basically that only.
Okay.
Yeah. Okay.
And what part of like what functions represent like which time complexity? Like let's say int, or let's say addition. Addition takes what time complexity?
Uh,
And
if you are adding two
for
integers, say
loops,
1 plus 2, that is like constant time. Like you do not need to perform any extra work, right? If you do 1 plus 2, you will just immediately get 3. Like there's no extra work there. Now say if you have two arrays, like say if you have an array 1, 2, 3, and you have some array 5, 6, 7, and then you want to add these two arrays, then in that case it's going to be O of n, right? Because you're going to have to go over each element and add them. So you'll get 5 plus 1, 6, and then 2 plus 6, 8, and then 3 plus 7, 10. So just if there are n elements, you'll have to, if you have n elements, you'll have to do this addition. You just basically n times O of 1, kind of. You can see it like that. So that will just give O of n. So yeah, in general, if you're just talking about adding two integers, that's just O of 1. Was I able to clear your doubt?
yes, yes.
Okay, okay. So yeah, so let's look at the next slide. Right, so now we are just going to just briefly talk about some examples. And in each example, we are going to work out what should be the big O time complexity of this program. So the first one I'm going to work out for you guys so that you guys have an idea of how to do it. And then the next one I will ask you guys to do it. Okay. So this first one, So what we have here is basically we have two nested for loops, right? So in the first for loop, we are going from I equals 1 to 1, 2, 3, 4, 5, 6, like this up to n we are going, right? In the second for loop, we are taking j from 1, 2, 3 up to n, right? Now, you will see that
Sure,
for
sorry to
each,
interrupt. Have you changed the slides?
yeah, like there are two pieces of code on the slides right now.
Like it's not visible to me at
Uh,
least.
it, it isn't. Uh,
No, it is
Yeah,
visible.
we are able to see.
Yes, we are able to see.
okay.
Network issues on my part, maybe.
Yeah, maybe it's a network issue on your end. Um, so just check your net, I guess. Anyway, the session is being recorded, so like you can check this part again later in the recording. Okay, so yeah, so in the inner for loop, as I said, we are going from 1 to 3, 1 to n. And now if you see, since it's a nested for loop, we are doing this part for each value of I, right? So when I is equals to 1, j is going from 1 to up to n. Again, when I is equals to 2, j is going from uh, 1 up to n. So, and this continues for another n times, right? So, what we see here is that here we are going over n steps, here we are going over n steps, and so on, we are going n steps. And this whole thing is being done n times. So what we have here is basically n times n equals n square. And of course, there is some constant associated with it because like we have integers and like we are going to be adding to those integers. So adding takes some time and just going over the for loop, just it takes some time. So like we'll just put in a constant for that. But basically this form you can write it as O of n square, right? Because you can recall the definition, and usually we drop the constants. Usually the constants, right? This constant c here, this doesn't matter to us. In some cases it does, like when you're doing some constant optimization with say bit sets, but that is quite advanced. So usually we don't care about this constant right here. So yeah, so it's c of n square, so we can just write it as O of n square, right? If you recall the definition. So yeah, this is O of n square. Do you guys have any doubts in how I did this?
Like, won't it charge some time when it go through two for loops, like uh, other than n square operations?
Yeah. So like, yeah. So it will take some time going to the. So basically, that's just going to be some c1 n square plus c2. It won't be any greater term like n cube, right? Because going over the for loop, like, um, yeah, it won't take n cube because like we are going over it only n square times. So like, where did this factor of extra n come from? We can just write it
Ah,
as like
yeah,
c1 n squared plus c2 because there is some time
because
associated with
we don't
say
know what it,
yeah.
because we need to consider definition of for loop, right? Like what how it is predefined in computer.
Yeah, so like initializing a for loop will take constant time only, na? Like when do you see a for loop taking like huge amounts of time to be set up?
Yeah,
Yeah, so like you will just set up I is equals to 1, that will take some time, and then I plus plus g plus plus. So like yeah, it will usually be of this form only, some kind of polynomial in n. And like we know as because of we can just pick some constant like c3 which is greater than c1, and then we'll just have this that like say g is equals to like if we pick gn equals to n square, and then we can see that c3 n square is greater than equals to this thing right here if we pick c3 greater than c1. So it's fine, we can write it as n square only. uh Okay, any other doubts? If you guys don't have any other doubts, I would like you all to start working this one out. And if you get the answer, please unmute and tell me. What do you think this should be?
This will be same like O of n square.
N square plus n.
O of n log n.
O
Uh,
of n square.
n into n
O,
plus 1 by
O of
2.
n square.
O of n square plus n.
okay. So yeah, all of you yeah, most of you are right. This will be O of n square only. Because like if you see like we are going from, you might think that okay, we are start going from 1 to n and then we are going from 2 to n. So like this we are doing n minus 1 n up to 1. So like this will be n into n plus 1 by 2. But then you see that you can just write it as half of n square plus n by 2. So like if you just pick so your gn equals to n square and set some constant c is equals to say 2. So 2 of n square will be greater than equals to this for some n naught. So yeah, that is right. You can take O of n square. Whoever said O of n square plus n, well, actually you can just replace that by n square only, because if you have n square and n square plus n, you can pick some constant such that n square will grow faster than like c1 n square will grow faster than n square plus n. So yeah, I mean, if you even if you put some constant c2 and c3, you can pick some large enough c1. So yeah, you can just write it as O of n square. So that's okay.
Yeah.
Yeah, okay. So next two examples. Okay, so uh, actually first let's try this one. Okay, so here we basically have this I into I means I square. I square less than equals to n is basically this thing. So can you guys tell me what should be the O for this?
O of square root n.
Root n.
Anyone else? Okay, so the two people who said O of square root n, they are right. Yeah, right. Because you will see that we are going from this is the wait, this is the number of steps we are taking. So we are taking 1, 2, 3, 4 up to some c, and at each step you will see one, then 1 squared, then 2 squared, then 3 squared, 4 squared up to c squared, and we will stop when we'll get some c. We'll get that c square is greater than or yeah, greater than n, right? So this will be the first at c2. So if we just rewrite this a bit, we'll get c is greater than root n. So
I think
basically,
greater integer function of root n, I think.
yeah, what did you say?
Greater integer function of root n, I think.
Yeah, like yeah, c is equals to like yeah, you can write it like that, greater integer, actually ceiling. So like yeah, we will stop at yeah, floor of root n, yeah. So basically you can just ignore this floor and yeah, so the number of steps we'll take is some like it's around root n. So if it's around root n, you can just write it as O of root n, right? Because again, we don't care about the constants. So yeah, this O of root n is correct. Okay, so now this program you will see is just basically if you are given some n equals 234, say for example, then what this does is this is the sum of digits. You're just finding out the sum of digits in base 10. Okay, so this program, what do you think the O should be?
Log 10. Log n to the base 10.
More than 2n should be fine.
Log n.
Mm, yeah, yeah. You guys are right. It will be. Wait, sorry. It will be O of log. n, or if you want, you can write it as of log base 10 also, but like uh, this like log base 10, and you can also write it as like log base 2 n over log base 2 10. So like this 1 by log 2 over 10 term, this is again a constant. So this is some constant C1. So any of these are fine actually. You can write log n or log base 10 and it doesn't matter. Because this conversion factor is going to be again a constant. So yeah, is that right?
Why will it
Okay.
be log n? Can you explain?
Can you repeat yourself?
Why will it be log n?
Oh, I meant log base 20. Yeah, it will be, you can write it as O of log base 2n. The reason is that you are making, say, a log of like some constant times log of base 10 times n. But then this thing, this log of 10, if you remember, like, I don't know which classes it is taught in, but like, you can just write it as, say, log base 2n over log base 2 10. Like, if there was a formula, like, I think
Yes,
log
this
a.
is okay. I was asking why will it be log n? Like I did not get how it will be log n.
Oh, okay. So, wait, let me just erase all this. Tell you how it's log n. So, basically, you see that in this while loop, while n is greater than 0, this you can just ignore. We are dividing n by 10 in every step, right? So first we are doing n by 10, and then we are doing n by 100, and so on. And so we'll get some n by 10 to the power k, where the floor of this will be equals to basically 0, since we are doing integer division. So at each step we will be taking the floor. So so basically you can just view this as we have 234. Then if we divide this by 10 and take the floor, we'll get 23, and then we'll get 2, and then we'll get 0. So you see that at each step we are basically removing one digit, right? So basically we just want to see, so what is the k for which 10 to the power k is some greater than n, right? So if you take log on both sides, you will get some k greater than log base 10 n. So that is basically how you get this log runtime. Did you understand?
Yes.
Hello, like I think my net just went away for a moment there. Uh,
Yes.
Hello, am I audible? Yes, okay. So like whoever was asking that doubt was able to make it clear.
Yes.
Okay. Okay, so now we will move on to the last example, which is maybe slightly tricky, but I hope you guys will at least will be able to do it. So this program right here, I assume all of you understand nested for loops well enough by now. So uh, what do you think the answer for this one will be? If you want me to explain the program once, I can do that. I'll just give you guys like 2 minutes to just think over this. I will give the answer at 6:41.
Is it n log n?
Is it n square?
Okay, so we have guesses. N log n square. These are guesses. Anyone else? Yes, can you repeat? N cube.
M cube. N cube.
Okay. Any other guesses?
N log 2.
Uh, I'm
Yeah.
I'm getting a sum, but I'm not able to evaluate that. Means it's harmonic sum, that's why.
Okay. Okay.
So OHN. ONH. N.
Of N H N. Where N is harmonic. Wait,
Yeah, mine
harmonic.
also same. ONHN.
Okay. Okay.
N log n.
Okay. So basically the same as this. Okay. So yeah. So basically the correct answer is actually this one. N natural logarithm of n, or you can write it as n log n. Does it matter? So yeah, so the question is why it is this. Like some of you guessed n square, maybe upon seeing two nested for loops. I do not know why some of you said n cube, but maybe you had some logic. So let me just explain why it is this one. Okay, so this one, say for I equals 1, you will see that the inner for loop is going like j equals 1, then 2, then 3, up to n. And you will see that this does this some n times. Okay, now if I is equals to 2, we will have j is equals to 1, then 3, then 5, and so on up to n. So this will, since it's going by 2 every time, you will see that this one takes n by 2 steps. Now, if you have I equals 3, it will take j1, then j plus equals 3, so 1, 4, plus 3, 7, up to n. So on, you will
I
see,
got an
yeah.
sorry for interruption, but I got a different answer. Like n plus ceiling of n plus ceiling of n by 2 plus ceiling of n by 3 till ceiling of n by n.
Uh, uh, in, yeah, that's okay, right? Like, ceiling of n by k is going to be,
Yes, yes, sigma ceiling of n by k from 1 to n.
yeah, so, okay. Yeah, that is okay, okay. Like, we don't,
This is similar to
doesn't,
NHN.
yeah, yeah. I mean, this sum and like just writing n by k, it's not really much of a big difference, I think, because like you can bound it above by some n by k is less than equals to say n by k plus 2, and then just do 2
Because
times and
actu-
yeah,
actually we are dealing with integers, so we can use discontinuous functions also. That's my opinion.
yeah, we can use discontinuous functions, but like the analysis of why this is O of n log n becomes much harder if you're dealing with say ceiling and floor. It's going to become much harder. I'm just saying you can drop this because anyway this holds true, and then you just have this kind of term, and your answer is like of a bigger complexity than this one. So I'm just saying it doesn't really matter what you like, what you take, but it would be nicer if we just took some continuous function only. It will just make our life easier. That's all I'm saying, and there is no problem in doing that. Let me just continue. So I mean, if we continue this, you'll just get the same pattern, n by 4 up to n by n. So yeah, so basically you will just get the sum uh, I equals 1 to n of n over k, and then you can write this as n times I of 1 over n, like this. Yeah. So yeah, as someone correctly pointed out, you will get the harmonic numbers. But what we really want to show is that how do we bound this? How do we bound the value of the harmonic of this harmonic series up to n? Right. So uh, uh, I'm just going to erase some of this so I can make space. If you don't mind.
What do you mean by bound the function?
Bound the function, I want to say that I want to get some function f of n such that for some like for some n such that for n greater than n naught, fn is always greater than equals to this sum. I just want it's like I want to give it an upper bound, like it's never going to be any greater than this. Okay,
Okay.
right. So yeah, I'm just going to erase this because I will need some space. Uh, okay, so yeah. Okay, so let's just I mean, if you guys have studied something called Riemann sum, converting sum to integral, then maybe it will be easier for you to see this. But let's just draw the graph of 1 over x, right? So if we draw this graph, uh, we have some, we have our 1 over x and we have x. So it's going to look like, say, like this. And at see here we have 1, here we have 2, then 3 up to n. Right, now let's just draw some rectangles. Okay, we're going to draw a rectangle like this, and this is going to be 1, you know, because 1 over 1 is 1. Then we are going to draw another rectangle like this. This is going to be at half, because value of the point of this function at 2 is 1 over 2. And similarly, we'll get 1 over 3, and then we'll get some 1 over n. And you will see that the width of each of these rectangles is 1 only. So basically, if you sum up these areas, you will get 1 over 1 times 1 plus 1 over 2 times 1 plus dot 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 up to 1 over n times 1. And you will see that this is basically our sum, whatever we got here. Whatever we got here, this is the same. Now, the trick we are going to apply here is we will see that we know how to do the integration of 1 over x dx. And what the integration will give us is actually this area right here. It will give us this area if we integrate from 1 to n, right? And then this area we can just add plus 1. And then you can see that there is some extra area over here that is left over. So we can safely say that this area that we are going to get, this is going to be, this is going to give an upper bound for the value of the sum. This sum of, I have been using I throughout. I really meant k. Uh, yeah, k. Right. So this integration we know how to perform. This is just going to be 1 plus ln of n minus ln of 1, which is just 0. So we have found out that this harmonic number hn is less than equals to 1 plus ln n. And again, we can just, you know, if we just multiply this with n, we'll get that this is less than equals to 1 plus ln n. So again, we can just drop the term which grows slower. So like, so again, for some n naught, this n ln n is going to be greater than equals to n. So basically, we can just write this as O of n ln n. And again, we can write it as O of n log n also if we want. So this is the proof of why it's n log n. If you guys had any difficulty in following, in any step, uh, feel free to ask right now. Also, I would like to point out that why I gave this example is that this example you will come across because using this for loop, you can find the divisors of all numbers up to n. Divisors of all numbers up to n. So like you go from, I guess, wait, I forgot the exact code, but yeah, you will see this later because like I think maybe next class we will teach number theory. There you will come across this for loop once again. So this is why I just included this example, and also because the complexity analysis is a little interesting because it involves the use of these Riemann sums. So yeah, that's what I wanted to point out. Any questions? If not, we'll just go to the next slide. So, if you guys have no more questions, yeah. So, I think we ended quite early. Uh, but here are some further topics you can read. You can read about the analysis of merge sort's time complexity. Merge sort is basically a method of sorting an array. So you take an array, you split it in half, you take these two arrays, then you split them also in half, and you keep going until you get one element arrays. And then while you're merging two arrays, like say like this, you check, you merge them in linear time, in O of n time, by just maintaining two pointers. Maybe some of you have heard of this before, I don't know, but you can just read about it in the net. The logic is fairly simple to follow. So yeah, any questions? Anybody ask something? Okay, so yeah, so basically you will see that the time complexity for this is given by a recurrence relation, like T of n is equals to 2 of T times n over 2 plus some O of n. And then you can apply some some maths and you can solve this recurrence relation and you'll get O of n log n. So you can see the analysis of this, it's quite interesting. And one more thing, which is even more advanced, which maybe you will not get at this point, but you can still just see once. It is called a master theorem. So this master theorem basically tells you, it generalizes this basically. It tells you what is the answer if you have Tn equals to A times Tn over B plus O of Fn. If you have this kind of recurrence relation, what is the complexity of this? It will just tell you. And one more thing you can look at is amortized analysis. Sounds difficult. You do. Hello. Am I audible? I think I lost my net again.
Your voice almost
Uh,
almost.
Hello. Am I audible now?
Yeah, yeah.
Okay. So yeah. So yeah, I was just talking about amortized analysis. Like basically, you will see that sometimes you have to do some very difficult operations, but it will turn out that you don't have to do them very often. So overall, when you sum over everything, so it will turn out that difficult operations are very uncommon. So their contribution to the final answer is very small. So we don't care about each step. Instead, we care about the overall result. In a way, you can say. So that is the like basic idea of amortized analysis. You can read about it. There are lecture videos also available on YouTube, on maybe MIT OpenCourseWare. You can see. So yeah, um, any questions before we end? Actually, we ended very early.
Hello, Dada.
Yeah, yeah.
Hello. Will we have the session every week on Wednesday, or will it be some random days?
Uh, Currently, what we think we'll do is we'll host classes twice every week. The next class is probably on Friday or on the weekend. We will decide on a specific like schedule over the next few weeks. We'll let you know.
Like Saturday we have exam like
Oh,
3
okay,
to 5
Saturday.
we have.
Okay, so if the session is taken from let's say 6 to 8, like is there a problem? Like, is there an exam on Sunday like, or is
6 to 8
everyone
is
willing
no
to attend?
problem, I think so. The exam is till 5:15.
Okay, so like also everyone is willing to attend sessions after 45 minutes after the exam, right? That's not an issue, right?
Yeah.
Okay, okay. So then I guess we can have a session from 6 to 7:30 on Saturday, I guess. And okay, we were thinking of
Will
Friday as an
C++
option, but if
basics be taught or should we learn them in hand? Hello.
it's better that you start learning C++ basics.
And I have a doubt like in what language are you going to code? Because I didn't attend starting 10 minutes.
I think we are going to code like if we are going to write code, we are going to do it in C++ only because that's most widely used. But for next class, actually, yeah, we will require some code rate. Yeah,
I mean, most of you
so
are
I
familiar
guess
with
you
C, right?
should learn at least some.
Yeah, actually we were taught C
Yeah, you are
in our
familiar
semester.
with the for loops, if statements, and like, mainly those two things of C, right?
Yes, yes.
Okay, so then it's not that big of a deal right now for the next class. Uh, we will be teaching STL later on, which contains some advanced topics in C++, but like basically the for loops and the if statements in C and C++ are identical, so you need not worry.
Will you be teaching STL in complete depth? Like, do we need to refer again, or will you cover it completely?
Complete depth is a strong term. I mean, yeah, like there is always something that can be learned.
Yeah, no one can cover STL completely, but yeah, we will be going over what you will be using most frequently. Like what is usually used, we will cover everything.
Okay.
Definitely.
Can you
Can you
avoid
avoid
keeping
keeping
sessions on
sessions
Wednesday
on
and
Wednesday and
Friday?
Friday?
Because the schedule is quite hectic and we also have TA on board.
Sorry, can you please repeat? It was not quite audible for me.
Can you avoid keeping sessions on Wednesday and Friday because the schedule is quite hectic and we also have EAA on board.
Is this true for every section? I mean, that is the question. Like, sure, we can keep it on some other days, but like keeping it on some other days and then some other group of people would say that they have their EAs on Tuesday. So, or maybe we can keep a poll whether Tuesday works or Thursday works, right? Mainak, what do you think?
Anything happens, we'll get the recording. Please record it.
Yes.
Like current days are fine. You can like people can see the recording.
What is a good platform to learn C++?
Mainak, can you answer that?
Um, mm, I think you can check out this site called learncpp.com. There is this site. And besides that, I think if you search on YouTube, C++, there is like a playlist of everything important in C++. Uh, yeah, so if you just search C++ basics playlist on YouTube, maybe you'll find, and there is this site called learncpp.com which covers everything in depth. Yeah, so far that much I know that these are available.
Okay, thanks.
So how long will this workshop be going on? Like 1 month, 2 month, or
Let's see, possibly 2 months, but yeah, let's see how it progresses. Okay.
Okay, right. One more thing that is important that I wanted to mention is that I would encourage all of you to start taking part in on CodeChef. You can start taking part in starters contests. On AtCoder, you can take part in AtCoder beginner contests or ABCs for short. And on CodeForces, you can take part in Division 3 rounds. So I would encourage all of you to start taking part in these rounds. Also, there is a CodeChef starters contest today, so do take part in it. It starts from 8 p.m. if you're free. Yeah.
Yeah, keep those in the chat box.
Okay, sure.
Yeah, like it'll help us. Like,
Okay, so if no one has any other questions, I think we can end it here. What do you think, Anubha?
Yes, also, please follow the Grammar of Code pages so that you can get updates. So you'll also post updates over here in Teams.
Post a link here also.
For
I posted.
okay, yeah, yeah, sure.
Okay, so
Yeah, so everyone, we have posted the links. I've posted the links to the contests that were recommended. Swapnil has posted the GOC Facebook, the link to the GOC Facebook page, and Shivansh has posted the starters contest that will be held tonight at 8 p.m. So everyone, please take part in this contest. It will be a great point to start your CP uh, as a whole. Okay, then if anyone has any general question regarding this workshop, any suggestion or any question regarding to what was taught today, please, you can unmute and speak right now.
so like you guys are in second year, right?
Yeah,
Yeah, I and Mainak are in second year.
I think most of the moderators here are in second year, except Priyam and Rishit.
Yeah, Prem and Rishit are third years. Okay, is there any more questions? Also, please ask if you have any question, because in the next lectures onwards, we will be assuming that you understood what was taught in this lecture, and we will blindly use those terms and results.
I think we can stop the recording also now.
Okay then, I'll be stopping the recording.